Okay, we'll see how far we get in the 5-3 notes. So we are going to continue just learning about some rules of how to calculate probability. Now, reminder, chapter 5 is only 3 sections long, so guess what? Okay, we're already there. we're already almost there. All right. So what we talked about yesterday was just some basic rules of how to calculate probability, and then we did the addition rule. So today we're going to talk about conditional probability and independence. Knowing the results of a previous event can affect the results of predicting a future event. The probability we assign to an event can change if we know something else has already occurred. This idea is key to many applications of probability. All right, so we call this conditional probability. The probability that one event happens given that another event is already known to have happened. Okay, pause.
Thank you.
Yeah.
Hi, my name is Ian Russell, and I am now the full-time counselor here at the Campus Center. You don't know those in a long, long time. I am here to assist you in whatever you might need. If you're having a bad day, if you need to talk to somebody, if you need some help with what you're going to do after high school, college application, scheduling, whatever it might be. You can come in and see me, and I will be coordinating with your homeschool counselors, so you'll have a team on your behalf. What else was I going to tell you? Sorry, I've been doing this all day. Give me just 1 second. Oh, in the next couple of days, I will send out to your teachers how to set up an appointment with me. We're going to do that electronically. And in the meantime, if you just wanted to drop in, I am in that back corner office, the one that sort of points towards the school store and is right next to the vending room in the back of the conference. You know what I'm talking about? Right on that corner.
As you're heading down towards the science classroom, that first office in the corner with the blinds usually all closed. That's her office right in there. So
Okay.
Okay.
All right.
And I can tell you, I've known Miss Merkel for a really, really, really long time. If you're from North, you probably recognize her. Okay. But you guys are so lucky. A, to have a counselor here at Payne Cow, because I know how hard it can be to see a counselor in your home schools because they're busy. And B, how lucky you are that you got Miss Merkel. Yeah.
Almost as lucky as you are to have for her.
Oh my gosh, what a nice lady. I've known Miss Merkel for a long, long time. She was the AP coordinator at North for many years. And before that, she was a math teacher. She actually started her teaching career at Payne Cow back before we even had an MST program. So, all right. So that'll be a great little add-on to our video right in there. Nice. Okay, anyways. So conditional probability. If you have two events, suppose you know that event A already happened, whatever you define event A to be. Then the probability that event B happens, given that event A has already happened, is denoted by, and how we read this out loud is, what is the probability of B given A? And that's how we read this, B given A. And what we're saying is we assume that A already happened. And if that impacts B, that's what we do. Now, sometimes you literally have to recalculate the probability. Other times it's just a matter of thinking it through. So I have the same two-way table that we had in the 5-2 notes about being a homeowner or not being a homeowner, being a high school graduate or not a high school graduate. And the first question I just said, suppose we choose a member of this sample at random. What is the probability that the person is a high school graduate? High school graduate. There are 300 out of 510. Okay, so the probability of being a high school graduate would be 310 out of 500. That is not conditional probability. That is basic probability, okay? We call this the probability of success over the total. And we say success is just simply that it matches the criteria that we're looking for. Now, part B says, suppose you know that the person is a homeowner. So you now know something ahead of time. So now if we know the person is a homeowner, we're not going to look at all 500. We're only going to look at those 340. Now, out of those 340, what is the probability that the person is a high school graduate, given the fact that we know that they are a homeowner? Well, what it means now is, again, we're not looking at all 500. We're only looking at 340. And now, how many possible ways can I be successful here? We're high school graduates. There are 221 out of those 340. Suppose you know the person is a high school graduate. What's the probability they're a homeowner? What's the probability that they are a homeowner, given the fact that we know they graduated from high school? Well, if you know that they graduated from high school, we're not looking at all 500. We're only going to be looking at those 310. And out of those 310, how many of them own their own home? 221. So I was showing you notation here. At the same time, I actually showed you how what happens instead of using that grand total as the denominator. And that question actually came up in my 4th hour yesterday when we were doing the questions back here. Someone said, will the denominator always be the grand total? And I said, well, on yesterday's, yes. On today's, not necessarily. Okay, but it still typically ends up being one of your marginal values. Okay. If knowing the outcome of a previous event does not impact later probabilities, then we call them independent events. So classic examples of independent events: flipping a coin. If you flip a coin, what's the probability you get heads? 1/2. When you flip again, it's still 1/2. Every single time you flip, it's like you start over. Okay, what happened on the last flip has no bearing on what's going to happen on the next flip. Tossing dice, same thing. You could roll a die and get a 3. Getting a 3 doesn't have any impact on what you're going to get next time. Okay? So I said, suppose you flip a coin and you toss a die. Define the events as follows. A is getting a head and B is getting a 6. Determine the probability. What is the probability of A? So what is the probability I get heads? 1/2. Probability of B. What's the probability I get a 6? 1 out of 6. Now, this one says, what's the probability that I get heads given the fact I already got a 6? Still 1/2. Getting a 6 on the die has no impact on what I'm going to get when I flip my coin. What is the probability of getting a 6 given the fact I flipped a coin and got heads? Okay, 1 out of 6. Now, I chose those examples because they're almost so extreme, they're obvious. Okay, what happens on the coin, what happens on the die, they're separate, they're independent. But what I want you to notice here is the probability of A and the probability of A given B were equal. The probability of B and the probability of B given A were equal. These right here are official formulas right here. These are tests for independence. They are not on the formula page, but you need to know them. You need to know that if these two things are equal, then A and B are independent. If these two things are equal, then A and B are independent. Now, people always ask me, do I have to do both? I often do just to be safe, but usually if they're not independent, it'll fail the first time, okay? So right there, definition of independent events. I'm going to put stars by these again. You need to know, not on the formula page. All right, so just to change it up a little bit, I now have a new two-way table. So remember, two-way tables are used when you have one group of individuals. So we have a group of 40 individuals, but we have them separated based on their gender. And we also have them separated based on, do they have allergies or do they not have allergies? So this might be an allergist is trying to decide whether there is some sort of relationship between gender and your, it doesn't really look like it, okay? The numbers actually are all fairly similar, okay? And we're going to eventually learn a way that we could actually conduct a test to find out if there is a relationship. But for right now, are the events female and allergies mutually exclusive? Now that was a terminology I gave you yesterday. Mutually exclusive means they cannot happen at the same time. Can someone be female and have allergies at the same time? Yeah, right there, there's 10 of them, okay? So are the events mutually exclusive? No, okay? Because there actually is, if I said, is there an overlap? Can someone be female and have allergies at the same time? Yes, okay? There are 10 of those people. Now, are they independent? When it comes to mutually exclusive, you literally can look at this table and say the fact that there is a number in the overlap, not mutually exclusive. For independence, you have to conduct the test. You have to start by saying, what is the probability of being female? Just in general. The probability of being female is 23 out of 40. And then what you have to do is you have to calculate the probability of being female given the fact that they have allergies. Now, if it's given the fact that they have allergies, we're not going to be looking out of 40. We're going to be looking at out of 18 because 18 people have allergies altogether. Now, out of those 18, how many are female? 10. And now what you have to ask yourself, is the probability of being female equal to the probability of being female given that you have allergies? Are those two things equal? 23 divided by 40, about 58%. 10 out of 18, only 56%. 58%, 56%, not equal. Now I get it, they were pretty close, okay? They were pretty close, and that's what this whole thing here is kind of talking about. Don't overthink it, okay? The fact is this was only a sample of 40 people, and we know that every time we conduct a random sample, things could come out to be slightly different. And you think, well, what if they took a bigger sample? Okay, there's a lot of things. Are these so close that they might be really equal? Maybe, but again, don't overthink it. I'm going to look at this and say those are not equal, not independent. Okay, now they are close enough. I maybe would try the other direction also. I maybe would say, well, what's the probability that someone has allergies? Allergies, there are 18 out of 40 people total. What's the probability that someone has allergies given the fact that they're female? Well, there are 23 females and 10 of those have allergies. Are those equal? 18 out of 40, 45%. 10 out of 23, 43%. So again, pretty close. But I'm going to say no, because I'm going to say that these are not equal and those were not equal. And I get it, they're close enough. I might be like maybe, but by definition, we're going to say no. Okay? Define two events as follows. Event A, you draw a red card from a deck of cards. Event B, you draw a spade. Are the events mutually exclusive? Is there any overlap between being a red card and being a spade? Is there any overlap? No. If you know anything about a deck of cards, you know that spades are all black, reds are hearts and diamonds, okay? There is nothing in this overlap. Are they mutually exclusive? They are. You either have a red card or you have a spade. You can't have one card that satisfies both, okay? Now, are they independent? What is the probability of A? What is the probability of A given B? And then we'll reverse it. What's the probability of B? What's the probability of B given A? All right, so A is red. Just in general, what is the probability you get a red card? It's half the deck, right? Okay, technically it's 26 out of 52. You could call it a half, whatever, okay? Now, what is the probability of A given B? So this says you draw a card. Okay, yeah, 0. Those are clearly not equal. And you could do the same thing here. You say probability of B. What's the probability that it's a spade? That's 13 out of 52. That's 1/4 of my deck. But if I draw one card, and it's already happened that I drew the card and it's red. So what is the probability that at the same time the card is also a spade? Of course, that's a 0. So are they independent? No, they are not. Now, I will tell you, it is really difficult for a lot of people to understand the difference of mutually exclusive and independence. Okay, it's very difficult. And what I tell people to do at this stage of the game is just learn this formula to test for independence. Mutually exclusive, you really can kind of just think through. Can it happen at the same time? Okay, independence, trust the formula. Okay, but now the last thing I want to talk about here is you will notice up here that we had not mutually exclusive and we had not independent. It can be neither. In this case, we had mutually exclusive, but not independent. It also can reverse. It could be not mutually exclusive, but it could be independent. But it can never be both. Okay? You guys know what pronouns are? Like I and me? Okay, so do you guys know the difference of where you use the word I in a sentence versus when you use the word me in a sentence? I am going to the store. You don't say me is going to the store. Okay? He brought the book to me. We don't say he brought the book to I, right? Now, the reason I do is it's a dumb little memory trick, but it's something I made up years ago. If me, then not I. You know that if the word me is appropriate in a sentence, you don't use the word I. If I, then not me. You know that if I is the correct word in a sentence, you can't replace it with me. So how does this relate to what we're doing? If events are mutually exclusive, then they will not be independent. If events are independent, then they will not be mutually exclusive. They can never be both. It can be one, it can be the other. Never both me and I at the same time. Never, never, never. It can be neither, like I showed you here. It can be yes to one, no to the other. It could be reversed. It can never be both. If me, then not I. Okay? Now that'll help you a little bit. If you identify that events are mutually exclusive, you will know, well, that it can't be independent. You wouldn't even have to conduct the test. You know it. Okay? All right, what's next? Oh, if events are independent, then you can apply what's called the multiplication rule. Because that's what you might be asking, like, why do I care? Why do I care if events are independent or not? Because you can apply the multiplication rule to find the probability of more than one event occurring. And if you want to find the probability, now this is the way it's usually written in textbooks. I actually also include the word then. I talk about A and then B. Because if you're talking about events happening in succession, right after the other, you're going to multiply as long as they're independent, okay? So you'll notice the word and gets associated with the intersection symbol, and it gets associated with multiplication, okay? So what I talked about yesterday was, I'm going to go back to the mutually exclusive work that we were doing. The union symbol is associated with addition and associated with the word or. And now basically what we're doing is we're talking about this part of the formula. So it actually does kind of relate to what we were doing yesterday. So what is the probability of getting heads when you toss a coin and then you roll a 6 on a standard die? All right, so, and I even put my little phrase and then to get you to think about it's one after the other. So if I want to find out what's the probability that I get heads and then I get a 6, those are independent. What happens on my coin and what happens on my die are completely independent of each other. So I can just take what is the probability of getting heads and I can multiply by the probability of getting a 6. Heads was 1/2, getting a 6 was 1 out of 6. So the probability that both things happen would be 1/12. And you'll notice when you multiply fractions, they get smaller, okay? Because the probability of getting heads is 1/2, but if I want that to happen and I want to get the 6, which only has a probability of 1/6, every time I want something else to happen, it reduces my overall probability that they all happen the way I want them to. And the nice thing about the multiplication rule is you could keep going. I could now say, okay, well, I flipped a penny on this one. What happens? What would be the probability that I flip a dime now and I get tails? Well, I could now say, and tails. Well, then I could take this and multiply by another 1/2, and now the answer would be 1/24. The multiplication rule, you can do as many things as you want, just one right after the other, as long as they're independent. If they're not independent, then we have to switch the second part of the formula. Instead of just the probability of A times the probability of B, you will now have to say the probability of B, assuming that A already happened. And that's the other way of thinking about that when we say B given A. What's the probability of B, assuming that A already happened? In example 3 on the previous page, 18 students in the sample of 40 suffered from allergies and 22 did not. Suppose you randomly select 2 students. Draw a tree diagram that models the sample space and find the probability that both students suffer from allergies. Now, you know what? I'm going to skip option A to begin with here. I'm just going to skip part A. Let's just do the probability. What is the probability that student 1 suffers from allergies and student 2 suffers from allergies? So I'm going to find what is the probability that the first student suffers from allergies. And that probability would be 18 out of 40. Now, what you have to think about though is now I have selected one of those students. You might remember doing this in Algebra 2 as we would talk about with or without replacement. So assume I'm picking 2 people that I want to test some medication on. So I've already selected my first person. So now how many are left? There's only 39 left. And how many are left with allergies? Only 17. You just did the conditional probability formula right there. You said, I'm going to multiply times the probability that the second student had allergies, assuming that I already picked the first one who had allergies. You actually did that formula. And then that would be your answer when you multiply those together. Now, where the tree diagram comes in, and you can do these, I like to do tree diagrams top to bottom. Your book goes sideways a lot. So I'm going to go sideways just to be like your book. So you don't need the tree diagram, but they do come in helpful at times. So we would start with all of our students, and we're going to split them into some have allergies, some do not have allergies. So when I first split my group, I could say that 18 out of 40 had allergies and 22 out of 40 did not have allergies. But then, assuming that you already chose, this is choosing person number 1 right here. Now I have to choose person number 2. Now the person number 2 could have allergies, or they might not have allergies. I want to put that there, not here. And here, the first person could have allergies, and the second one might not have allergies. So you can label your tree diagram. Now I'll zoom in a little bit here. So following through on this tree diagram, you actually did this path right here. You said if I started with 18 out of 40 who had allergies, then it would go down to only 17 out of 39 who had allergies. If you took one of these 18 out of 40, how many are left without allergies? Okay, still 22 non-allergies, but now out of 39 people. And then down here, 22 out of 40 did not have allergies. So let's assume I picked one of those. How many people are left who have allergies? That would now be 18 out of 39. Because if I follow this path, I'm assuming I picked someone who didn't have allergies. And down here, if I picked someone with no allergies, and now I want to pick someone else without allergies, it would be 21 out of 39. The benefit of the tree diagram is you could go through any of those paths. We chose just this path because it matched what the question was asking. But if you follow this path, this would be, what's the probability you pick someone who has allergies and then you pick someone who does not have allergies? What's the probability you pick someone who does not have allergies and then you pick someone who does? What's the probability you pick nobody has allergies? Here to here. So when you make the tree diagram, you can find all the different paths and choose the one that matches what you want. Okay, what if I said, what's the probability I just picked someone, one person who has allergies? Well, all of a sudden, allergies, no allergies. This path would work. No allergies, allergies. This path would work. There are 2 paths where only one person has allergies. Okay? We'll get more into the tree diagrams. Might not be today, that might be tomorrow. But all right, we'll finish this page and we'll stop here for today. When a probability question uses the phrase at least, it may be useful to apply the complement, and we did these in Algebra 2. The first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine, approximately 5% of normal pregnancies will receive positive results, called a false positive. Okay, picture what that means. Guys, I get it. Hard for you to picture being pregnant, but okay, even if someday you're married, your wife is pregnant, and you go and you get this test done, and they tell you you tested positive. They detected a chromosomal abnormality. Can you picture the stress that you must feel? Okay, and what they're saying is 5% of normal pregnancies get a false positive. So can you picture that 5% of normal pregnancies, they're all stressed, and they find out, oh, oops, okay, it happens, okay? If 20 women with normal pregnancies are tested, what is the probability that none of them will receive test results that are false positive? So this would fit into what we're doing right now, because we'll assume every woman is independent of another. They come in to get the test done. What happens on the first woman is not going to impact the second one. But on the first one, what is the probability that nobody gets a false positive? No false positive. What's the probability that the first woman does not get a false positive? What's the probability that she does not get a false positive? Okay, 5% get a false positive, so 95% don't get a false positive. All right, and then the next woman walks in. What's the probability that woman does not get a false positive? It's not a trick question. It's actually a really easy one. It's still 95%. I said every woman is independent of another. And if there's 20 women in a row, can you picture what this is going to look like? The same thing over and over. And because they're independent, and I want the first woman, and then the second woman, and then the third one, all you have to do then is multiply all of these together. How many of these are we going to multiply together? 20 of them, which a shorter way to do that is, how about we just take 0.95 and raise it to the 20th power? I had that comes out to be 0.358. Now, you have to understand what that 36% represents. Nobody got a false positive. But if there's a 5% chance of getting a false positive, couldn't you picture someone along the way maybe did? Okay. So that's the next question. If 20 women with normal pregnancies are tested, what is the probability that at least one of them does get a false positive? Now, I want you to think about what that means. Okay, this one is just 0.95 20 times in a row. At least one of them gets a false positive. So maybe this one gets a 5% instead. Or maybe this one gets a 5% instead. Or maybe the third one, or the fourth one, or the fifth one. And it says only at least one of them. So maybe the first and the second get the 5%, and the rest get 95%. Maybe the first and the 17th get 5%, and the rest get 95%. Or maybe they all get 5% except for one of them has the 95%. When it says at least one, you have to picture that 5% could be anywhere in the list, and it could be there once, or twice, or 3 times, or 4 times, and it could be anywhere. It could be moving all over. Can you picture how many places that 5% could fill in? This is not easy to calculate, what I would call in a forward direction. What we're going to do is the reverse. We're going to find what is the probability that there are no false positives. Oh, wait, we already did that. And we're going to do the complement of that. The probability of at least one false positive is going to be 1 minus the 0.358, which will give me 0.642. So there's a 36% chance that they all come clean. None of them get that 5%. None of them get the false positive. And there's a 64% chance, however, that at least one of them does. Okay, at least one. That could be 1 or 2 or 3 or 19. All right, and we will start tomorrow with